Okay, so now we're going to look at the case where you have more than one parameters, more than one parameter, right? So if you have more than one unknown quantity, we have to specify a joint distribution. So meaning we have to have a joint likelihood, joint prior, and then we will obtain a joint posterior. Okay, so for example, if you have a theta, so theta is a vector now, right? Theta is a vector. So theta can be p-dimensional. So p-dimensional means it has p parameters inside. Okay, and if we specify a joint prior, right, and combine with the data, so you can see over here, right, the posterior is actually a posterior for all p parameters, right? And then we have the likelihood, joint likelihood for the p parameters also, and we have the prior for the p parameters. Okay, so meaning that if you want to do this, we have to specify the likelihood for all the parameters and a prior for all the parameters, right? And we get a joint posterior for all the parameters also. Okay, so when you specify, actually there's a few ways, right, how you want to specify the parameters depending on your assumption, right? As the assumption, for example, right, you can assume the parameters are independent or things like that, right? So if you have to specify that, then that you can actually build that in inside your prior and also your likelihood. Okay. All right. So we have the most common one, which is again our normal. So before, right, if you see in our examples and also in our tutorials, we always have the normal likelihood, and then we have the parameters which are the mean and the variance. Okay, so before, because when we have only one parameter, we assume, like for the example, we assume mean is unknown, variance is known, or we assume that variance is unknown, mean is known, right? So either one, right? So if you have two parameters, so if you want to use the univariate version, right, you have to state that one of the parameters are actually constant or a known value, the known value, right? So, but what if we were to look at the normal data and we assume both the mean and the variance are unknown? Okay, so now we have our normal, right? So we assume both the mean and the variance are unknown, right? So now our unknown parameters are mu and phi, right? So phi is your variance. Okay, so here, as I said before, right, to make it easier to write, we usually don't use sigma square. We just use like one parameter. So here we use phi, right? So now we have the non-informative, which is also the improper prior, right? Okay, so here when you have the improper prior, so the first one is obviously it does not integrate to one, right? Because remember, right, when you have this, right, your mu is between minus infinity to infinity, right? And your sigma is positive, right? Because it's your variance, right? And if you were to integrate this, then okay, so because here again you assume prior independence. So what does it mean, right? So it means actually, right, your mu we assume, for example, is 1, and right, maybe not mu, your p mu is 1, right, and then your p phi is actually 1 over phi, right? Okay, so you can see over here, right, that and since, right, your mu is infinity, right, and your phi is bigger than 0, right? So in the first case, right, because mu is from minus infinity to infinity, if you integrate 1, so this is already improper because your mu, your 1 does not, does not integrate to 1, right? And also 1 over sigma square, 1 over phi also will not integrate to 1. So both are actually improper priors, okay? And because we assume a prior independence, right? That's why we multiply these two, right? This why these two we multiply and we got a joint prior, which is 1 over phi. So this is actually a joint prior for mu and phi, okay? So how we get it? Yeah, because we assume they are independent. The mu and phi are independent, so we multiply and we can get a joint prior for mu and phi. Okay, right. So then with the normal, right, we can get the likelihood, okay, which is this one. Okay, we can see, I'll see later how we get that. And then, right, and if you multiply your posterior, sorry, your likelihood with your prior, then you obtain your posterior. Okay, so here Y bar and S is as defined. This one is for easier for you to write, because if it's too long to write the summation. Okay, so how do you get the likelihood, right? So the likelihood is you obtain only after you do some wait, is there a space here? You only get after you do some simplification and manipulation, right? Okay. Okay, so if you look at your joint PDF for normal, oh, sorry, it's not, right? It should be your fee, right? So you have to multiply. Okay, so by the end of this course, or even middle of the course, you should be good. I mean, you should be very good in finding the likelihood, right? So we have our PDF for normal. Okay, so you have to simplify this, right? And we have this, right? And then we have this exponential. Okay, so this exponential part, right? You actually have to simplify and you have to open the summation, because this is exponential, right? After you multiply, it's actually summation. So you will have it's a summation, right? 5 from 1 to n. Okay, and it's actually yi minus mu. So this one actually, what happened is I will put in my y bar. Okay, so y bar is actually I minus and I add y bar, right? Okay, so there are steps here, right? So you actually will get to the next step because there are some assumption, right? So if you look at the proportional, then you can further simplify. The 2 pi is not there, right? And then you have this part, okay? And I have to have a bracket, right? And then you have y bar minus mu square. Okay, so there are actually steps inside in between, right? The two, because you can think of this as a plus b square, right? So you have a square plus, so this is a square plus 2ab plus b square. So this is your a square and this is your b square, right? So actually the 2ab, if this is your, so if this is your a, right, and this is your b, so 2ab actually will, the sum of 2ab is actually equal to 0. All right, so there are steps here. All right, the 2ab is actually equal to 0. That's why you can simplify from here to here. Then you get a square plus b square. Okay, and this is actually the just now the PDF for this is your S. So this is your S, right? Okay, and then you have your y bar minus mu, this part. Okay. Right. And this is S square, sorry. And then you can, and you can, and this one is actually your n y bar, wait. is actually n. After you simplify, you get your n minus of y bar minus mu. Yeah. So the sum, all right, the sum. So you get this is the s, this is the n y bar minus mu square. Okay. So then that's how you get your likelihood, right? And then as you say, as you can see, then you multiply with your prior, which is the 1 over phi, and then you get this posterior, right? And this is actually sometimes called the normal inverse gamma distribution. Okay, and we can see later why it's called a normal inverse gamma, because the conditional distribution of mu and phi are actually normal and inverse gamma. Okay, so we can see that also in the next chapter. Right. Okay. So, okay, one thing to note, right? If we were to have more than one parameter, sometimes you are only interested about a subset or one of them, right? So we can actually include just a subset of the parameters and not all of them, right? So parameters which we have no interest, sometimes are called nuisance parameters, and sometimes we don't want this nuisance. We want to get rid of them, but because they are not constant, right? We have to integrate them out, right? Meaning that you have to find the marginal posterior of the interesting or the parameters of interest. So you have to integrate out the nuisance parameters, right? So for example, if we have a subset which is theta 1 and theta 2, right? So we are interested in theta 1, so the theta 2 are nuisance. So what happened here is we only want to get the posterior of theta 1 only, right? So we have to integrate out the nuisance parameters theta 2. Okay. So for example, if we were to have our just now our normal data with our prior, which is 1 over phi, right? We have the joint posterior, so this is the same as before. Okay, so what happens if we want to we only want mu inside the distribution, right? So we only want the posterior of mu given y. So we have to integrate out. So you can see here, we have to integrate out our phi. So your phi is from 0 to infinity. Okay, and this is called the marginal posterior. So just now we have the joint posterior. So now we can actually find the marginal posterior of mu by integrating out your phi, right? And so this will actually involve a lot, well, not a lot, but some integration, right? So again, our course, we have a lot of integration going on and differentiation. Okay, so then, so if we want to find the marginal posterior, right? Okay, so, because this is up to proportionality, right? So we have to integrate. Okay, so to make it easier, right, you can actually, just rewrite or not rewrite, but make it into a constant or a function. Okay, so here, because first, okay, your inside here, this is not a constant because you have mu, right? But then because it's too long to write, I just put this as a, right? So this is a. So this a will come out later, right? This is to make it easier to write. Because when you integrate, we only integrate against phi, right? So the phi is your parameter now. This a is a constant for now. Okay. So then if we have this, right? So what happened here? If you rewrite this a bit, right? And then we have this form, and then we have this. Okay, so this is actually So what is this? This is actually the kernel of inverse gamma. So this is actually the kernel of inverse gamma, right? And then the parameter is actually n over 2 and a over 2. Okay, so you have the kernel of the inverse gamma. Okay, so to make this into a PDF, so you have to remember you have to multiply with a constant, because this is only proportional, right? It's not up to it does not integrate to 1 because it's not a full PDF. So you have to add in the constant to make it into a proper PDF, right? So this is actually again is long, right? Okay, so we have this. Okay, so this is actually the inverse of the 1 over, because you have to add and you have to multiply the inverse. Okay, so this is actually this, right? Okay, so this means that you multiply with this whole thing. This is the reverse, so it's actually your this, right? And then you have the reverse, then multiply with this, right? And again the phi, and this will actually will integrate to 1. Okay, so you meaning that you have, because this is a kernel, right? As I say, it's not a proper PDF, so you have to multiply with a constant and then multiply the reverse as a constant. So actually this one will become 1. But this is actually a PDF of inverse gamma, so this one will integrate to 1. Okay, and this you are left with the leftover constant. Okay, right. And then okay, so if we were to open this, so this one already integrate to 1. So if you were to take this out, okay, so now right, you can see over here that now your A here, okay, your A here, it comes out again because now you have your mu inside it. Okay, and this n over 2 is a constant, so again this one is proportional. So we have our A, so A, we have, is it A over 2? Oh, okay. Right, so we have S, this is your A, right? S y bar minus mu, okay, minus n over 2. Right, okay, so then we have this. Okay, again, and of course, 2 also is a constant, right? If you take out the 2 outside, it's 1 over 2 power n minus 2, so you can get it, the 2 is also multiplied by A multiplied by 2, so 2 is also a constant, that's why you don't see anymore. So you only left with, this is your A, the original A, and then you multiply, you have power minus n over 2. Okay, so then if we rearrange again, so we have this, right, divided by S. So again is a constant. Okay, and okay, so this is where it involves a bit more, because you have to actually fit it to I'll call it, you have to fit it to a T distribution, right? And this is called a non-central T distribution. Okay, so if we were to again rearrange it, like this, I think, mu minus y bar square divided by S over, okay, and then we have n minus 1 plus 1 over 2. Okay, so if we have this, right, so this will be actually, then this is actually a non-central T distribution, right? And you have T minus 1 degrees of freedom. So the mean here is y bar, and the variance is S and minus 1. Okay, so this is where you have to rearrange, right? Your mu minus y bar, because mu is your parameter, right? So y bar is the mean here, and then the variance here is your at the bottom is s n minus 1. So I add n minus 1, n minus 1. This one you can actually cancel out, right? And the n I just bring down, right? So then you get this, okay? Or if you can, this is a non-central non-central t distribution, right? But if you want to have a t distribution, you can minus the mean and divide by the standard deviation. Sorry, the square root, I think. I think this is, sorry, this is, okay, I think I have to check. The S, is it the mean, the variance or the standard deviation? Okay. So I think I have to check that, whether it's a standard deviation or the variance. Okay, so but if you divide by, I think this might be the standard deviation, because if you divide by S star, then mu minus y bar and divide by S star over n, then you have a t distribution with n minus 1 degrees of freedom. Right here, the S star is your S n minus 1. Okay, so it should be the standard deviation. Okay, so I'll check that. Okay, I'll check that after this. Okay, so anyway, so we have, so meaning that if I were to find the marginal posterior for mu, right, then the mu will have a non-central t distribution, okay, with these two parameters. Okay, right. So, okay, wait, maybe, wait, I think I have that distribution. Let me see. There's non-central, so it should be V. Okay, then it should be the sigma square. Then it should be the variance, I think. It's not. Okay, so if you can see, right, this, if you have a non-central t distribution, then we have the mu is the location and sigma square is the variance. Okay, right. So you can see, right, yeah. So this is where you need to move around. Then you have, okay, V1 minus V, wait, should be N. Okay, right. Sigma square. Oh, okay. Ah, right. Okay, right. Yeah, I think we probably have to, okay. Do you think we have to rearrange into this form? Anyway, all right, you can see that, yeah, sigma, then you have the N, yeah, okay, right. So this is, yeah, anyway, this is the, the non-central T distribution, right? So you can see that the, yeah, it needs a bit maneuvering to actually obtain that from just now. Okay, right. So anyway, going back. Okay, right. So anyway, and actually, so the other option is actually to have a conjugate prior, right? But actually, conjugate priors are more difficult to work with, right? For more than one parameter, because they are not usually independent. Okay, but the principles are the same, right? For example, if you have the conjugate prior for normal, right, which is for mean and variance unknown, so we have it very long, right? And then we have this. So this conjugate prior is actually have the same distribution as your likelihood, which is the normal inverse gamma, right? And then this one, actually we can write it as mu given phi is normal, right? And then phi is inverse gamma, right? Then your prior of mu, joint prior of mu and phi is just the conditional prior of mu multiplied by prior of phi. Okay, so then you will get this conjugate prior, which is the normal inverse gamma, right? But usually it's quite hard to actually find a conjugate prior because it will involve more than one parameter. Okay, so it's not so easy to use as the univariate case. Right. Okay, so for the predictive distribution, right, in the case of multivariate, is actually similar as the univariate, right? Meaning that if you have, for example, you have n parameters, right? So you have to multiply, so you have to integrate out all n parameters. So if you have the future observation z given your data y, right? So you have to find the uh, you have to find the distribution, right? And then which is the likelihood of z multiplied by posterior of theta, and then you have to integrate out all your parameters theta 1 to theta n. Okay, and just again take note, right? If your prior is discrete, then you have to multiply the integrals with the summation. Right? For example, if you have theta 1 is continuous and theta 2 is discrete, then you have to integrate out your, you have to sum up your theta 2 because it's a discrete, right? And then you have to integrate your theta 1 because it's continuous. Okay, right. So that's the end for the prior chapter. Okay, so do you have any question, class? No, class, no question. Right? Okay. All right. So if there is no question, then we will just continue on to the next chapter. Yes. Okay. Right. So this is what I think some of you have been asking about, right? How do we actually do the computation part, right? And you can see that actually there are a few ways, right? How you can actually estimate the parameter values, right? Of course, the most popular one is the MCMC Markov-Chain Monte Carlo, but apart from that, there are actually other ways, right? So the first way is we can use approximation. Okay, also before that, right? Just saying like, why do we actually need this sampling? Right, because sometimes, right, when you have when you get the posterior, it might not be a non-distribution, especially if you have more than one parameter, right? You only get a density, right? So the density might not be a proper distribution, or might be a joint density of more than one parameter. So it's hard to work with, right? And then so in practice, usually Bayesian requires a lot of computation, right? Because you want to get sample from the posterior, but you cannot use them directly because you cannot, it's not a non-distribution. Okay. Of course, the one that we have used before are all sufficiently convenient form because we only get the nice distribution, right? But if you don't get the nice distribution, then we cannot sample from them directly, right? Because we have a more complex model, right? Which is more logical when we work with real data, right? And then because we specify the prior distribution, right? Which the actual, which actually reflect the true prior, right? Apart rather than using a prior which is convenient, right? So this will actually lead to your posterior being more complicated than that we have learned before. right? So if you have distributions which are complex and high dimensional, then we actually need some computation tools, right, for sampling. Okay, and just take note, right? So usually what happens with the posterior is that's why we always have the proportional, right? So when you have our posterior, we always write proportional, right? So meaning, but if we were to write properly with the proper density, right, then we always have to have to be equal. So with the equal one, we have to have the constant, right? Constant multiplied by your density, right? And this is called the normalizing constant. Okay, and then because if the um, density is complicated, right? Usually this normalizing constant is actually unknown and hard to find out. Okay, so if you want to use this as a proper distribution, it's hard because first it's complicated. Two, you don't know your normalizing constant C. C is unknown, right? So what happened here is whenever we do the computation part of the Bayesian, we try to use computation techniques which do not require you to know your C. So even though C is unknown, you can still do your sampling or you can still do your approximation. Okay, so this is when you choose your method, usually the advantage is you don't need to know your C. So even though you know your density up to some unknown constant, you don't need to know the constant. Okay, so some of the some of the method does not require you to know your C. So that's the advantage. Okay, so the first method is the normal approximation, right? So this is obviously not very not very logical if your density is not symmetric, right? But we can use it if your posterior is unimodal, only have one mode, and roughly symmetric. Okay, roughly symmetric, right? Meaning that roughly, right, approximately symmetric, and only have one mode. We can approximate by using a multivariate normal. Okay, so but of course, when you want to approximate by using normal, you have to know the mean and variance, right? Meaning you have to have the posterior, and you have to get a good approximation of the normal. Then you have to get the mean and variance from the true distribution or the true posterior, right? But because the posterior is not tractable, right? So usually, if you don't know the distribution, right, it's hard to find the mean and variance of the distribution, right? Because it's unknown, right? So finding the true mean and variance for the posterior might be hard, right? So again, because we say approximation, we try to approximate, right, by using the Taylor expansion of log posterior about the mode. So now we are looking at the mode. So because this is the unimodal, right? So we are looking, instead of the mean, we are looking at the mode, which we call the theta tilde. Okay, the mode means that if you have the top, right? So the mode is the value of x where it's at the top here. So this is your mode. Okay, so it might not be symmetric, so it might be skewed, but we are looking at the highest density which correspond to the mode. Okay, so to do this, right, we look at we're going to use the Taylor's expansion, okay, of the log posterior. Okay, so if well, you don't know, but the Taylor one-dimensional Taylor series for a function g about x naught. So you have your g here. So we have g x naught, and then you can expand it, and then this is first derivative, right? And then if you power r and r factorial, this is the r derivative and so on. Okay, so meaning that we can go from 0 and then 1 derivative up to r, right? But of course, this is if you're looking at the Taylor series expansion, right? But usually if you were to use it for approximation, you only use up to two, up to two differentiation. Okay, up to R equals to 2 actually. Okay, right. So if you look over here, right? So if you have, for example, right, if your x is equal to your parameter is your theta, and then your x naught, right? The point here, x naught is your mode, right? So this is your mode, right? And your g is the log of your posterior. Okay, so then you have this is gx, and then you have the differentiate your gx once, and then differentiate gx twice. Okay, so we only go up to second differentiation, right? Because our assumption is, this is our assumption, right? The assumption is the remaining terms of the terraces will be small when theta is close to your mode and n is large, right? So meaning that if your theta is close to the mode and you have a large sample, then the third derivative and so on will be small. Okay, so that's why, so actually we have plus ... So we assume it to be small, so we can disregard the rest of the Taylor series. Okay, so this is one, that's why it's using the approximation here, because this is just an approximation, assuming that the rest of the series are small and is negligible. Okay, so then we're going to look at, so we have the first, we have this log of the P at the mode. Okay, so this is actually a constant, right? This is actually a constant. And then we have a first function, right? And then so this, okay, what does this notation means? This means that you differentiate your log posterior against theta, and then theta is equal to the mode, right? After you differentiate, then you equal theta equal to your theta tilde. Sorry. Okay. So, and this is, you differentiate twice, right? You differentiate twice, and then after you differentiate twice, then you equate theta equal to theta tilde. Okay, right? So after, how can I move it? All right. So after you have, if you look at it, right, and you simplify, okay, and all right. So here, okay, here this, all right. So actually this one, right, it be equal to 0, right? Because remember, yeah, theta is your mode, right? So we assume, right, as you remember, we assume the mode is the highest point, right? And if you differentiate your log posterior, right, and then you equal to the mode, right? Remember, right, it's similar to the MLE, that the mode will actually maximize your log posterior, right? So if you differentiate your log posterior and then you theta equal to your mode, then this first derivative will be equal to 0. This one, right, equal to 0. Okay, so this one will be equal to 0 because is maximized. You should be maximized at the mode. Okay, right. So this means that you only have this plus the second derivative, right? And because your log p theta tilde is a constant, so you can have a proportional of your second derivative multiplied by a function of theta. Okay, and if you and because this is a log, right? Remember, this is a log of your posterior. So if you move the log to exponential, then you have this exponential of this function, right? And you can see, right, you have exponential. You can add minus, right? So how does the minus comes in? You introduce the minus here at the observed information, right? The I theta, you have minus here. You have minus here, right? That's why you have minus here at the exponential, right? And then your theta, the information is the second derivative, right? And then you put it down here, and then because that's why it become inverse here, right? Okay, and then you have, and then if you look at this at this exponential function is very similar to a normal kernel, right? So you have this is your, if you have a normal kernel, this would be your mean, right? And this would be your variance, right? The normal kernel. Okay. So, right, that's why because it looks like a normal kernel, that's why we use the normal approximation, right? Approximate, right? And here means that if you were to use a normal approximation, then it will have a mean of the mode theta tilde, and then the inverse, sorry, the variance is actually your observed information I theta at the mode theta tilde. Okay, and if we have a multivariate, then we have a vector theta, right? And so this will be a vector, and this will be a matrix. Okay, right. Wait, I think, right. So, okay, so what if we look at example? Okay, so example, we have a data which is come from a Poisson distribution with parameter lambda. Okay, and we have uniform prior on lambda. So lambda is again a improper prior. And then we want to find a normal approximation to the posterior distribution. Okay, so one thing to note, right? Because oh yeah, sorry, not this one. Oh, okay. So now we will so this means, right, you have your, okay, so this one you should find, you should know how to find already. So you have your prior, and then you have your likelihood, right, and your posterior. Okay, and just you can try to find on your own, but the posterior of lambda given y is actually, I think this is also we've seen in the examples and also your tutorials. Right, we have this. Okay, right. Yeah, S is the sum of your yi. Okay, and if you have a true distribution, right, this is actually a gamma. So actually you know the true distribution, right? But this is good if you want to compare with the approximation, right? So we have gamma, S plus 1, and we have N, okay? But then this is your posterior, okay? And then you have your, so one good thing is, you can actually find the proportional, you can only use the proportional, because when you do this anyway, you can see that, right, you can find the log posterior up to proportionality. Okay, so then you have your log posterior, then right, then you have to find the information, observed information. So you have to differentiate log posterior again, right, and then differentiate twice. Okay, and then your observed information. Okay, so one thing, right? So your observed information, remember, is at, so your observed information is actually, it should be S over lambda square, right? Okay, so what is the mode, right? So again, right, the mode we can find by using the log first derivative, right? Remember, because I said that the log, so the mode should maximize your first derivative, right? So then you get from the first derivative here, then you get S over lambda minus N equals to 0. Then you get your mode is equal to S over N. Okay, then you have your first your observed information. Then you have your observed information at your mode, right? And then you replace the lambda with your R tilde, right? So you have n square over s. Okay, so meaning that you from the first derivative you can find your mode, and then from the second derivative you can find your observed information, but then it's observed at your mode, so you have to replace the parameter with the observed mode, then you have the observed information. Okay, so this means that if I have if I have a normal approximation, right, it should be approximately normal. Then we have the mean. The mean is our mode, S over n, and the variance is, remember, right, the variance is the inverse of your I, so it will be S over n square. Okay, so it's the inverse of your I inverse. So I inverse is S over n square. Okay, right. So one thing, right, if you want to look at this approximation, right, because we actually can get our true distribution, right, because your lambda is actually gamma, right, S plus 1 over n. So we can actually compare with your real mean and variance, right? So if you have your real one, right, your mean is your expectation from the posterior, right? So this is actually because it's a gamma, so you can get alpha over beta, which is s plus 1 over n. Okay, or if we write it, it will be like this. Okay, and the variance of your posterior is alpha over beta square. So you have this, and or if you write, you get this. Okay, so you can see, right? So you can see that the approximate mean and variance at the mode and the real mean and variance are actually quite close, right? The difference is only with some function, right? But you can see, right, this one, right, that this actually will go to this as your n increases, right? Meaning that as your n increases, the approximation will be better, right? The version will get better as your n increases, because you can see, right, as your n increases, the second part here, right, as your n increases, this part, right, and this part will go to 0, right, as n gets very large. So as your n gets very large, then this part will go to 0. So your true and your approximate mean and variance will actually be very close. Okay, so meaning that this normal approximation will be better as your n gets larger. Okay. So so this is where I say that depends on the sample size. Okay, it will also depend on your sample size of your posterior distribution. Okay, right. So that is the first way, right? Meaning that we use the posterior sampling. Okay. So the second way is actually to use, the first way is to use the normal approximation. So the second way is actually to use a posterior sampling. So there are actually various ways for posterior sampling, right? And the most basic one is, of course, to use the Monte Carlo integration, right? Because when you use posterior sampling, means that you sample from some distribution, right? And you want to use the sample, right, to estimate the value or the properties of the distribution, right? For example, mean, variance, quantile, intervals, and so on. Credible interval, right? Okay, so this is also used in the MCNC part, The first one is called, the basic one is the Monte Carlo integration, right? So for example, we want to estimate a function f. So what happened here is we have to, when you want to estimate the function f as an expectation of fx, so we have to have a density px, right? So we integrate against the PDF px, right? And so if you use the Monte Carlo sampling, it means that you're actually using the estimator, which is the average, right? So this is actually called the Monte Carlo sample average method, because you're using the average of the sample. Okay, so the idea here is you sample from the density, right? You sample from the density, right? And you have to calculate the function fx, all right? And you sample, for example, you have to sample n values, right? And you calculate your fx for each value, and then you get the average over the number of samples, n, with n. Okay, so the sample average will actually be an approximate for your mean of the expected value of the function. Okay, and this will be actually an unbiased estimator, because the expected of the estimator is equal to your expected of the true function, right? And then you have the variance. Okay, meaning that if you have a large sample size, the variance of estimator will decrease. Okay, so that is the simple one, right? The not simple, I mean the basic one. So the other way you can use Monte Carlo is called the importance sampling. So here, for example, we want to estimate the function fx against the PDF p, but p is hard to generate sample from. Okay, but we actually can use another distribution, q, which is easier to sample from, and which is called an approximation to p, right? For example, right, your p can be complicated, right? You can use, for example, your q can be the normal distribution, right? So what happened here, originally we have fxpx, so we add your q at the top and bottom, right? So now this is your new function, and this is actually a function against your PDF, which is your qx. Okay, so take note, right? In this case, right, the range of values for your q and your p should be the same, right, or similar. Okay, so to make it more efficient, right? Because when you integrate, right, you integrate of your x, the x value should match for the q and for the p. So anyway, so you have your new function now, and you integrate against your q. So this is actually an expression against q now, right? So when you do the Monte Carlo, you actually sample from the q, right? So qx are actually sample from q. Okay, so then now the new function is this, and then you get the average of this new function, and sum over 1 over n, and then this is the estimator of your expectation of your fx. Okay, and take note, right, if your q and your p are equal, right, then you just get back your normal Monte Carlo sampling. Right, so again, we can show that this I hat is a unbiased estimator, right? But the variance is again depend on the sample size n. Okay, so if we so maybe you can look at an example, right? So suppose that we have the example from before, right? We want to sample from this Poisson, but we want to use the normal approximation as our sampler. Okay, so what does it mean, right? It means that you have, okay, so one thing, right? So, but one thing about using auto sampling that you should know is this will actually involve that you need to know the true PDF. Okay, because right, if you look at this function, right, this is actually integration of against the PDF of the distribution. So meaning that you actually have to know the PDF given to the constant, because you want to integrate, right? Okay, so this is a bit the part where you cannot use approximation. Okay, right. But of course, for the sample you can. But I mean, for the P, the original P, then you have to have use the full PDF, right? So from our previous example 5.1, right? We know that your posterior is actually a gamma, right? So you can actually get the full PDF, right, which is the gamma. Okay. Okay, so this is again, right? So that then you want to use your approximation is your Q, right? So your Q here from the previous example, your QX. Well, should I use X? Oh, okay, we can't. All right, so you're using X or you're using Y. Well, I guess it's easier to okay. I mean, it's actually using Y, right? So QY is normal. So you have your mean, which is your mean and your variance of the normal. Okay, so then you actually need to write the actual PDF of the normal, right? The full one, which is the long version. Wait, oh yeah. Okay, right, and then very long, and then minus 2s over n square. All right. Okay, right. Okay, but of course, because it's a normal approximation, actually, you can actually, if we use, okay. So if I were to generate from standard normal, right? If I were to generate from standard normal, then actually I can get, right, for example, I generate from U is from standard normal 0, 1. Okay, so I can get my, oh sorry, it's not. Why? Okay, that's why it's very strange. Okay, so it's not, because we want to generate, so it's actually lambda. Okay, I was thinking there's something weird going on. Okay, so this is actually your lambda, because we have to generate lambda, right? So it's actually lambda. Okay, right? So then if you get uniform 0, 1, you can actually get lambda from your uniform, sorry, normal 0, 1, not uniform 0, 1. Your normal 0, 1, you can actually get lambda from your from normal 0, 1, and then you can get normal with the mean and variance, which is not 0, 1. Okay, so this is the part where it's going to be long, right? So when you have the approximation, right? So when you have your I, right, which your I, right? You want to find the expectation, right? So what happened here is, okay, Oh, right. Wait. What is the question? Mean. Okay, so you want to find the mean, right? The mean important sampler for the mean. Okay. So the mean means that you want to find the expectation of your lambda, mean of lambda. Okay. So if you were to write it, it will be actually lambda times the posterior, right, of lambda. This is the original. Okay. But then, so this one, meaning that this is against your posterior, right? This is against your posterior, your P. Okay. But now if we were to use our Q, right? So it would be an expression against Q. Then we have, so your lambda is your F, right? Your fx, the function. Then you have your lambda multiplied by Q, right? Q lambda, right? So this is will be expectation against Q, right? And this would be, and then the estimator, right? The estimator would be the average 1 over, if you have n samples, one from 1 to n, then you have the, you have to actually calculate the function Q lambda I. Okay, the average of for this function. Okay, and the function is actually long. Long means that you have to divide. So what happened here is, oh, okay, this is in lambda. Okay, so what happened here, you have to divide your P, right? So meaning you have to divide, this is your P, divide your P with your Q. This function, this whole function, divide by this whole function. Okay, you cannot take out any, you cannot simplify. Okay, this is one thing about the input sampling, because when you, if you look over here, right, we have the because it's expectation, right? So you must put in any constant inside also. So that's why it's quite long, right? Of course, you can simplify, but you have to simplify if it's cancelled out, right? If it doesn't cancel out, you cannot take it out. So you cannot use up to proportionality, because this will need exact value. Okay, right? Because it's too long for me to write. So anyway, it will be this P. So number 1, right? Divide by number 2. This whole function you divide. Okay, right? And then, so it will be that function. So it will be the sum of lambda I. So that function 1 divided by the function 2. Huh? Sorry?
Doctor, can I ask you a question?
Okay, sorry. Yes.
Yeah, actually, I just wanted to check for the posterior distribution, the P lambda given Y, right? For the formula, I'm not sure whether the power for the exponential, is it e to the power of minus negative nx or negative y? I just wanted to check that.
Oh, this one.
For the, is it nx or ny?
Sorry. Okay. There's actually lambda actually. Okay,
Oh,
my
okay.
writing is very bad. Okay, sorry. This is lambda. See, I know my lambda and my S and my, yeah, it looks very similar. Sorry, class.
Okay.
So lambda.
Okay, thank you.
We were wondering why. Okay. Yeah, so it's lambda. Okay, I've
Okay,
tried
thank
to
you.
look. Okay, I see my, I think this, okay, this is lambda also. Lambda is normal. Okay, correct. Lambda. Yeah, maybe lambda is not a good thing to write, because lambda and that, yeah, it looks very similar. Okay, that one is lambda. Okay, right. So going back. So because very long to write. So it's actually number 1 divided by number 2 is function. So you have to calculate, right? Right. So this one will need a computer to do this, right? So you can see, right, that if you use the computer, then if I would, okay, so the true mean, right, because here, right, because here you actually have to put in your data. Okay, so to actually calculate this, you have to put in your data because as he asked just now, right? Because you have the S, right, and you have your N. So to actually calculate this, you have to give a value. I mean, you have to put in the data and get a proper distribution. Then only you can do the calculation by computer, right? So maybe I don't know, for exercise we can do that, right? For example, if you use your N is 10, right, and your S is 30 lah for illustration purpose, right? So if you use this, right, you can get your true mean is actually your true posterior mean is actually 3.1. Okay, so we can actually try, and if you were to do this Monte Carlo simulation, right, you can find that if I use I had and if I use my N is actually 10,000, right, I can get my estimate as 3.1, well, close 3.1 or 3.10 something lah, right? Not really exactly. So you would actually need the Monte Carlo for 10,000 sampling to get a similar value as the true mean. Okay, so this one is in theory lah. So I think maybe, I'm not sure, maybe for exercise or later we can actually try this. Because, but yeah, the thing is you have to type out all this function. Okay, this function 1 and function 2, you have to type out. So that's the long. Unless we have we could also use the density in R actually. Right. Yeah, actually we can use the density in R. All right. So anyway, right. Oh, I think we probably have to stop after this. Okay, right. So before we stop, right? So I'm just going to talk a little bit about this Monte Carlo because I'm not going to the theory here I put in, right? But I'm not going to discuss all the theoretical part. This is just for you to so when you have time after this you can read through it. But the important part for the Monte Carlo is just that first is the Markov chain property, right? And then the number 2 is the convergence, right? So that's the most convergence to a distribution. So that is the important part when we're doing the MCMC Markov chain Monte Carlo. Okay, so when you, because the people who have time after this, you can read the theoretical part, right? Okay, and so the first part is okay, so the technique, this is the important part, right? We have MCMC, so you have to construct a chain, right? And the posterior will be a stationary distribution. Okay, what does it mean by stationary distribution? Meaning that if you run this Markov chain for a long time, the Markov chain will converge to the stationary distribution. And we have to construct it such that the stationary distribution is our posterior distribution that we want to target. Okay, right? And our aim is from some starting point, meaning that any starting point, right? If we run the Markov chain long enough, it will converge, and then it will get the sample from our posterior that we want. Okay, after we run it for a long time. Okay, and after it has converged means that the sample are now sample from the posterior. Then after you get the sample from the posterior, as if you get sample from the posterior, then you can use the sample to estimate the properties. For example, the mean, the interval, and so on. Okay, so all the result means that you have to build this MCMC such that it will converge, and the convergence is towards your posterior that we want. Okay, so that is the main idea behind the MCMC. Okay, right? And of course, the first part would be what is Markov chain, right? So the Markov chain, so when you have Markov chain, the sample will not be independent sample, right? Because Markov chain, you can see over here, Markov chains means the current value depend on the previous value. Okay, so your xt depend on your st minus 1. So the sample from the Markov chain are not independent. They are actually correlated. The t is correlated with t minus 1. So they are not independent sample. Okay, however, your t, meaning that your t minus, meaning they are only correlated with the t minus 1. So meaning that your xt and the xt minus 2, xt minus 3, the past x3, x3 minus 4, and before that, this one, they are independent. Given, right? Given you know xt minus 1. So given xt minus 1, this xt and the past are actually independent. So xt only depends on xt minus 1. Okay, so this is the Markov chain. This is the Markov chain behavior. All right. So given the current value, the future only depend. Sorry, the future is independent of the past. So xt is independent of xt minus 2, 3, 4, and so on, given that you know xt minus 1. Okay, so even though they are correlated only by one time space or time step. Okay, so this is a Markov chain. Right, and then you have the transition kernel. Okay, so whenever you have notation of transition kernel, this is when you want to move from xt minus 1 to xt minus 1 to xt. Right, so this is how you write the transition kernel. Okay, or if you have a continuous, then we have the integrated. Okay, right. So this part is where I say, right, this part you can read on your own. Blah blah blah. You have definition a lot. Okay. Okay, so this is the part where is actually the most important part here is the convergence. Right. So meaning that if you have all the properties of this Markov chain, then you have a stationary distribution pi, then this Markov chain will actually converge to pi as t goes to infinity. So as time goes on, this Markov chain will converge to the stationary distribution pi. Okay, so this is what we want, right? We want this important part. And what did I? Oh, okay. And because also this is where you have to end. If you have Markov chain, and if we have a sample mean, will converge to the expectation. This is also where we use the Monte Carlo part, right? Because under Monte Carlo sample average method, the mean will converge to the expectation. So if I have a function f, then the sample mean of the function will converge to the expectation of the function under pi, under our stationary distribution. Okay, so the main idea here is this. So this paragraph contain the main idea of our Markov chain Monte Carlo, right? Meaning that we have to construct a Markov chain such that the posterior will be the stationary distribution. So this is the point, right? Posterior, or we call the target, will be the stationary distribution, right? So we can start from any initial point, and if you run the chain long enough, we will get sample from the posterior. Okay, so this this is the paragraph is where the main idea of the Markov chain MCMC comes in. Okay, so meaning that if we have a large number of iteration or a large number of samples, right, it does not depend on the initial starting point. It's independent of the initial starting point, meaning that you doesn't matter where you start. If you run your Markov chain long enough or your MCMC long enough, it will actually sample from your posterior or your target distribution. Okay, so the average will converge to their expectation under the target distribution. Okay, so I think I will stop now, right? So for those who have time, you can look over all the definition and so on. Okay, right, and